So just let me know whenever you guys want to start. All right. Are we good to go? All right. So today we continue our second of three lectures on cosmology. And let's begin by just recapping where we are in our cosmic plan here. We're tackling a lot of these questions of great relevance, ultimately, to particle physics, dark matter, dark energy, super high energy, stuff we can learn from studying our Big Bang as a physics lab, etc. And again, as I mentioned yesterday, if you want to hear more about wilder aspects of cosmology, parallel universes and that kind of stuff, that won't be in these lectures, but the organizers invited me to give a public lecture about that tonight, which is going to be where exactly again? Z1b20, yeah, okay. And last time I said that I find it very convenient to take this huge subject of cosmology and organize all the material by different orders of perturbation theory. So the zeroth order, we think of everything in our universe as being completely uniform. The density, the temperature, everything is independent of position. So we don't have any partial differential equations, just ordinary differential equations. We just have all this stuff evolving gradually with time, and we started working through a bunch of stuff related to that. Today, I hope we'll get started also on first order. And I also want to spend a fair bit of time today talking about measurements, because cosmology, again, has transformed from being very flaky and speculative to being a really data-driven field. And I want to give you a quick survey of some of the amazing different types of data that are out there, so you can fully appreciate what they might be able to do for you in your various particle physics pursuits. All right? So to summarize what we did last time, we talked about the history of our universe. What we know so far is that during the past 13.7 billion years, there are these two different processes which have been going on. Things have been gradually expanding, which has transformed this very dense gas to something much more rarefied. It's transformed things from being very hot to being very cold, all because of the expansion. And moreover, there's a second process, a transition from being boring and uniform almost to being very clumpy and interesting. Okay? And this growth of clustering, we're going to use first order perturbation theory to be more quantitative about and understand what we can extract from that. We then got more quantitative. We did a bunch of stuff on the board. We started with Einstein's field equations and general relativity and showed how this uniform universe is described by the Friedmann-Robertson-Walker metric. And there's this one free function in it, a of t, which just basically tells us the size of our universe as a function of time. And we solved it for a number of different interesting cases, and we see that our actual universe seems to have first been expanding exponentially nearly in the beginning, or early on, during what we call inflation. Then it's chilled out, it slowed down, and just was dominated by radiation, relativistic particles, at which time this function a went like the square root of time. And then eventually the radiation diluted faster than the ordinary stuff, and we got dominated by ordinary matter. And then the expansion went only like the 2/3 power of time. And then more recently, at about half the present age, dark energy started making up more than half of all the density in our universe, which doesn't seem to dilute at all, triggering another phase of accelerated expansion, which we're heading into now. Okay? When we look back in space, as we discussed, our universe, we see younger and younger and smaller galaxies in the distance, and then we see none at all because they haven't formed yet. And at the very far end of this, we see this faint glow, the cosmic microwave background. And if you may, I can do a little bit of magic with this. I'm going to actually pass the universe on to you, so you can have a little fun with it. Because when we look at this, when you look back, at this time when the plasma is hot enough to be when the hydrogen is hot enough to be an ionized plasma, we can no longer see through it. It's opaque, right? And it looks like we're staring at an opaque wall. So behind the galaxies, you see this opaque wall like this. But of course, it's going to look that way whatever direction in space we choose to appear, right? So it looks to us actually as if beyond all the galaxies, we're surrounded by this opaque plasma sphere. We're seeing it from the inside. Okay? Even though, of course, when you plot it like this, it looks like we're from the outside. But we're in the center. We're looking at the interior of this. And we can take pictures of this plasma sphere with great precision. The Planck, I'll tell you a bit more about the Planck satellite, which gave the most amazing pictures of this to date. And this has been extremely useful for us because these pictures are baby pictures of our universe in the sense that they photograph the way things were about 400,000 years after our Big Bang. Ridiculously long ago. And these patterns we see here, I like to think of it as the cosmic DNA in the sense that the slight fluctuations in density here at the level of 10 to the minus 5 encode the information that will later determine how our universe grows. Galaxies will form in the places where there's a little bit more density, and giant voids will form in places where there's a little bit less density. Just like our DNA when we were babies determined whether, how tall we were going to get and what eye color we would have, etc. If we peel off the surface here to see what's inside this volume, which we usually call our observable universe, or just our universe for short, because by definition it's all that we can actually see, even with the best imaginable telescopes, then what's inside? Thank you, Maya. So here is our universe. Don't break it. We need to take care not of just of Earth, but of our universe. But you're welcome to pass it around, as long as you make sure it doesn't land on any pointy object. What you see here from this picture is that, although that's very cool, that data, it's mainly just information from this inside surface here. Right? We're looking along our backward light cone. We would love to ultimately get more information about what's going on everywhere in this. To complement this, we have looked very hard with telescopes at galaxies and other stuff we can see. And the biggest galaxy maps that we have so far, that I flew you around in at the beginning of yesterday's lecture, are making up just this little dinky volume in the center here. Okay? So our universe that you're passing around here is huge. Okay? The vast majority of it is still very unknown. It's sort of like this country before the Lewis and Clark expedition. There was a lot known about the eastern seaboard, and then people had sailed over to the Pacific and knew a bit about that. People had very little clue what was sort of in the vast swaths of the interior, like Boulder, for example. And I'm going to talk more about another technique, 21 centimeter tomography, that we've been having a lot of fun with in my group to try to fill in the missing parts here. If you label this a little quantitatively with redshift that we talked about last time, this is what you get. It's a redshift of about 1100 at the micro background surface. So the light that we see has a wavelength which is 1100 times longer. If it says redshift 3, for example, remember you're supposed to take 1 plus z and get 4. It means the space was 4 times smaller. So waves coming from redshift 3 have 4 times as long wavelength as they do now. If we instead put times there, we solved the Friedmann equation last time in class, right? And worked out how big our universe is, what A, the scale factor is as a function of redshift, or as a function of time. So we can draw in time here. This is what it looks like. We see that about halfway over to the edge, it's already 13 billion years ago, 12, 13 billion years ago. So most of the volume is actually very, very, very long ago. I want to do a little bit more math now so we can get more quantitative about connecting this qualitative stuff with all the precision measurements that are coming along, okay? So you have really good tools for calculating things. So let's begin by pulling this down and just reminding ourselves that we had our Friedmann equation, right, which said that the square of the expansion rate, square of the Hubble parameter, was just 8 pi g over 3 times the total density of everything. Where this total density included, in the way we wrote things, the density of all the different components of stuff we have. They included radiation, which I'm going to write as rho sub gamma, so any relativistic particles. And that, how did that dilute as a function of A, did I say? Someone remember? Exactly, this went like a to the minus 4. And then we had matter, baryons and dark matter. And how did that dilute? Very good, 8 to the minus 3. And then I threw in curvature here also into this, which we saw that goes like a to the minus 2. Well, you can have a plus or a minus sign. And then finally, you seem to have some kind of dark energy, which is just constant. Okay? So this is just a recap of what we did last time. Now, when doing math with this in practice, it's very convenient to define a little bit more notation. And rewrite this as follows. So if we just write this as h0 squared times a giant parenthesis, where h0 is just whatever the value is of the Hubble parameter today. Okay? And then rewrite the 4 terms here. So if you look at this, let's look at this function h as a function of a. It's a sum of 4 terms, a to the minus 4, a to the minus 3, a to the minus 2, and 1, right? We remember that the redshift is just 1 plus z is just the inverse of this. So it's actually just a 4th order polynomial, a quartic polynomial in redshift is all this really is. And that's nice because that means we can actually write down how fast our universe expanded at some given redshift just algebraically without having to solve any kind of differential equation, without even solving the Friedmann equation at all. So let's write this quartic polynomial more explicitly. So there is a 1 plus z to the 4th quartic term, corresponding to a to the minus 4 here, right? And then we're going to call the prefactor here omega sub gamma. So if you just compare this with this, that implicitly defines what this constant has to be. And we'll come back and talk about it in a second. But it's just some number that you can go measure, which is dimensionless, in fact. And then we have omega matter times 1 plus redshift cubed plus omega curvature times 1 plus redshift squared plus omega lambda times no powers of the redshift. Okay? So here you have your quartic polynomial in 1 plus z. And if you just stare at these definitions a bit, it's convenient to also define something called the critical density. I'm going to write it as rho star. And we just define that as 3 times the Hubble parameter today squared over 8 pi g. So if you measure how fast our universe is expanding, which we've done, it gives you magic density here. And then we just define all these omega gamma, omega matter, omega curvature, and omega lambda. Apologies for losing the lambda. As the corresponding density component divided by the critical density. So I here could be gamma or m or k or lambda, okay? And if you look at this just from these definitions, it's first of all clear that if you just sum up all the different densities, you're going to get the critical density automatically. Because here's an equal sign here by definition. And moreover, that means that if you sum up all these omegas, all 4 of them, you always get 1. It's just an identity. Sometimes we also define omega total to be just the sum of the omegas of what you might think of as some kind of stuff. everything except curvature. So you could say omega total is omega gamma plus omega matter plus omega lambda. And then you see that equals, by definition, 1 minus k here. Okay? And we've measured, as I'll come back to, that this omega total is super close to 1, to better than 1%. Okay? So this is so far just definitions. Why do we define this? Basically because it's very annoying to have to always quote numbers that are like 10 to the minus. You don't want to talk about, we measure the density to be something times 10 to the minus 26 kilograms per cubic meter. It's more convenient to have numbers of order unity. And these are dimensionless also, these omegas. Okay? Now once you have these omegas, a lot of the math, in fact all of the math pretty much for anything you want to compute, can be worked out pretty easily in terms of them. For example, let's take a look at the age of our universe. So we see here in this plot, right, at different redshifts. At each redshift, we would like to know, okay, how old was our universe then? Okay? How do you do that? How do you find out how old our universe was at redshift 3? You can see from the picture, well, it was about 11 billion years. But how do you do that? The easiest way is to just solve the full Friedmann equation again. We did that yesterday for some special cases, but you don't actually need to, because it turns out that the Friedmann equation is just first order, and I'll show you how you can just reduce this to a simple integral in this case, if all you want is the age. So let's take A0, today's size of our universe, divided by A at some earlier time, which, remember, by definition was equal to 1 plus z here, okay? So if we just take the log of this, it tells us that the log of A0 minus log of A equals log of 1 plus z, right? So if I just differentiate this, and d log A is just minus d log 1 plus z. Okay? We'll just use that in a moment here. And then let's take the Hubble parameter again. And just remember that one of the ways of writing it is as d log A dt, which is A dot over A, right? And remind ourselves, what were we trying to accomplish? We were trying to figure out the time, the age of our universe, t, right? So we can take this expression and say, okay, dt, which we're going to, must then equal d log A over h, okay? So if I want to know how much time elapsed between two different redshifts, like between today, redshift 0, and redshift 3, for example, all I need to do is integrate this. Integrate dt. So I'm going to integrate d log A over h. We already had h as a very convenient algebraic function of z, right? It was a quartic polynomial of z. So let's eliminate a in favor of z using this on a line right above it. So we get minus integral d log 1 plus z over h. And then what's d log 1 plus z? It's, of course, just dz over 1 plus z. And we have our h, which we can think of just as some known function of z, namely the one that we wrote here above. And then there's a minus sign. I integrated from smaller a to bigger a, which is the same as going from bigger redshift to smaller redshift. So if I flip the order of integration and I go from the lower redshift to the higher redshift, then I remove the minus sign. And there you have it. That's the age of our universe. How you calculate the age of our universe. So to be a little bit more explicit, I may just raise up the screen enough that we can see what we had. To get h of z, we just take the square root of this thing here. So we get h, ultimately not inverse. The integral, if you want to know how old the universe was at some other redshift in the past, I can integrate from 0 up until that redshift. And then we integrate dz prime, 1 plus z prime, h of z prime, which is the square root of omega gamma, 1 plus z to the 4th, plus omega matter, 1 plus z cubed, plus omega curvature, 1 plus z squared, plus omega lambda. And the reason there's an H inverse here is because of that. Okay? So this is one example of how you can, without much work at all, just start using this formalism to relate stuff you measure, like, to the underlying theory, once you know these cosmological parameters. Okay? There should be little primes on these z's. And what we'll, in the next 15 minutes, we'll see that pretty much everything else that we care about, also the 0th order in our universe, how bright things look or how big they look, and so on, also can be reduced to some other kind of integral over redshift of this function h of z. And then the game that we want to play is we don't actually know a priori what h of z was, right? We would love to know this function, because if we know it, we can unpack the quartic polynomial and figure out what's the how much matter, what is omega matter, what is omega gamma, what is omega lambda, etc. And because we can, if you could see, for example, conveniently, a whole bunch of giant clocks out there in space at different redshifts, which each showed how old our universe was right now, then we'd already be done. You could just take pictures of these different clocks and use this formula to predict what each clock should show, at its redshift, and then keep adjusting these 4 parameters here until you get a good fit, and you would have measured these numbers. Unfortunately, nature hasn't been quite that kind. It provides us with some ways of estimating how old stars are and stuff, but there are other things I'm going to tell you about now, where you can measure things which you can fit to other integrals like this, which are super helpful. For example, we see all these objects out there. Galaxies, quasars, which are very bright, right? And we can measure, we've measured, for example, in our Sloan Digital Sky Survey projects, over 100 million objects and processed them in automated ways. We don't have quite the data rate of the LHC, but we have some pretty serious data sets in astronomy now. Oh no, our universe has undergone deflation. Can you rescue our universe, Maya? Thank you so much. Our universe can, of course, contract also. That's also a solution to the Friedmann equation, but not the one we seem to live in. So anyway, for each of these objects that we see with our telescopes, there are 2 quantities in particular that are very easy to, or interesting to try to measure. One is how dim they are compared to what they would look like nearby, and the other is how redshifted they are. Okay. The redshift is the easier part. So if you see any kind of spectral lines that you recognize, oh, that's hydrogen or that's a sodium line or whatever, you can immediately figure out the redshift. So you know what factor the universe had expanded by since light was given off. The dimming is a bit trickier. But if you imagine for a moment that you see something in your telescope, which is a giant light bulb, okay, and it says 100 watts printed on it, then you know exactly how much energy it's putting out, then you can compare with how dim and actually or bright it looks and figure out how far away it is, right? We do that all the time here with the inverse square law. If you see a car in the distance, double the distance, the tail lights will look exactly 4 times fainter. In an expanding universe, not surprising, this inverse square law gets a little bit modified. Okay, and I'll derive it and I'll show you what it turns into in a moment. But then nature has also provided us with a lot of things where it's kind of like a 100-watt bulb, which we astronomers call standard candles. There are certain objects like exploding supernovae, for instance, of type 1a, where we actually have a very good idea of how many watts they put out. The type 1a supernova involves a neutron star. Sorry, it involves a white dwarf, a dead star, which is orbiting around the companion star. Our sun is going to turn into a white dwarf, but it's a bachelor. But most stars come in pairs. Okay? So this other star and the neutron star are orbiting around each other. And as the other star starts to die and it bloats up and puffs up and gives off and pushes a lot of its gas out into space, more and more gas starts raining onto the neutron star. And Subramanya and Chandrasekhar famously proved that a neutron star cannot weigh more than 1.4 times as much as the sun. The famous Chandrasekhar limit. So as more and more stuff starts piling on this, when it reaches that, eventually it'll reach this maximum mass it's allowed to have, and it goes boom and explodes. That's a type 1a supernova. So all of these cosmic bombs all weigh roughly the same. So it's not too surprising that they're all also roughly equally bright because of this. There's very slight variations depending on the detailed composition of how many atoms you had of different kinds in there. But astronomers have developed some very good techniques for calibrating that out by also looking at how fast the explosion happened and the detailed colors of it. And the Nobel Prize was, of course, given for this just the other year for the discovery of dark energy, for exactly perfecting this technique, looking at these supernovae, figuring out exactly how many watts they were actually putting out. Okay, and when you do this game, you have a lot of objects, and you take the redshift and the brightness of each one, and you plot them against each other. You get a very interesting relation. When you look at things fairly near Earth, what you find is roughly a straight line on a log-log plot here, or even on a linear plot, actually. If you've converted the dimming into a distance. Why is that? Because we derived already in yesterday's lecture Hubble's law, that you expect the velocity with which something is receding from us to be proportional to its distance. But when you start going farther away, this is no longer a straight line, and the detailed shape of this curve is super interesting, and is also going to tell us something about all these omegas and the makeup of our universe. How? In the interest of time, I'm not going to do the full derivation of this. I'm just going to write down the formulas. But you're going to see they look very similar to this in the sense that it's going to be an integral of something to do with h at different redshifts again. Okay? So basically what we're heading towards here is we want a toolbox for getting by in curved space-time. We want some tools that connect the basic theory, the Friedmann equation, these omega parameters, into all the stuff that we can measure. Okay? So suppose we are here. And we're looking out into space, and we look at some stuff far, far away here. These objects that we look at are typically much smaller than in size than the distance they have from us. Okay? Suppose we consider a little volume of space here. So suppose it has there's some distance from the near edge of it to the far edge in the direction perpendicular to the line of sight. In parallel to the line of sight. So I'm writing two parallel lines here. And then it has some dimensions perpendicular to the line of sight like this. Alternatively, we can choose to talk about the redshift, the difference in redshift between the near end and the far end. If we're looking, for example, at a whole bunch of galaxies, we can measure the redshift of the most distant one and subtract off the redshift of the closest one. Then we're looking at this thing, and we like to relate these physical properties of it to what we measure. We measure, for example, that it subtends some angle, delta theta. Right? How big does it look in the sky? Euclid tells us that if you look at the angle that my chalk subtends to you, it's just in the small angle limit going to go like 1 over the distance. But we want to see how does that work in an expanding universe. It's going to get generalized, right? We also want to know if this is putting out some number of watts, how bright is it going to look to us? So let me, without further ado, just write down some helpful tools here, some helpful formulas. So first of all, we have the radial size. So this thing is measured in meters. If you think about what's happening here, we are really looking, if I do a little inset, along, if space weren't expanding, we would just be looking back along our backward light cone. And there would be some little object here. And there would be a little delta t here and a little delta r here. It says how far away it is. So the actual, the actual radial extent of it simply comes out to be this delta t here times the speed of light, because we're looking along the backward light cone, even in the GR case. And when you plug in what this is, we already have an expression for delta t here above that we worked out when we did the age of our universe. We just plug it in, and we get c h naught inverse. Sorry. C delta dz, 1 plus the redshift, and then we get this h of z coming in. An even more important thing is the angular size of things. One of you asked me yesterday, how do we know really how far away something is? So if you had some kind of standard ruler in space, if you knew how big a certain galaxy was in meters, for example, right, then if you knew the formula, how to convert the angle it subtends in the sky to how big it actually is, that will all depend on the distance to it, and you can then solve for the distance somehow. If space were not expanding at all, then we would just say that the actual size of it is just equal to the distance to it, right, times the angle that it subtends in the small angle limit. That's just Euclidean space, right? So what we do to be lazy in astronomy is we just define a quantity. We call it the angular diameter distance, which has the property that it behaves exactly like you would like it to. So it's a more complicated thing. It depends on redshift in a complicated way. I'll show you in a moment. But once you know the angular diameter distance to something, then you immediately know how to convert between the angular size and the distance, because one is just because the actual real size is just the angle that subtends times this. Okay. So the million-dollar question is, what is this angular diameter distance? And I'm going to skip the actual derivation. You can find it, for example, in Weinberg's book, because I want to show you some of the actual data that we use this for, and preserve a little bit of time for that. But here's the formula. C h naught inverse divided by 1 plus z. And then it gets a little more complicated. You have a function s, k, which I'll explain what it is in a second, of the absolute value of the omega curvature that we've talked about, square rooted, times another function, gamma of z. And then the whole thing gets divided again by the square root of this absolute value of the curvature parameter. And now I owe you some definitions. This S thing is either a sine or a sinh, depending on the curvature of space. So it's equal to sinh of x if this omega k thing here is positive. So and it's equal to sine x if this thing is negative, if a universe is sort of spherically curving back on itself, and if you take and it's equal to just x itself, if space is flat. Okay. And finally, I have to tell you the definition of this gamma. This function gamma of z is something that looks a little bit like this. It's an integral of the cosmic expansion history. It's the integral of from 0 to z of the Hubble parameter today divided by the Hubble parameter in the past, dz prime. So if you compare this with the integral for the age, what's the difference really? Other than the stupid constant theory. Yeah? Yeah? Ah, good question. So I'll get to that in a sec. So first of all, I just want to say that the only difference between this gamma of z and the age of universe, different z, you can see is here there is another redshift in the denominator, 1 plus z here. Here there isn't. So you're just taking, in both cases, you're integrating 1 over h, but with sort of different redshift weighting. And then what happens here in the case where omega k goes to 0? Oh, yeah, what you said here is, yeah, if you take omega curvature approaching 0, then what's going to happen is this omega thing will cancel out the omega thing in the denominator. And let's just write out exactly what happens. So flat space. So if omega k equals 0, then dA of z simplifies a little bit to just be equal to ch naught inverse over 1 plus z times just gamma of z. All the curvature stuff just quietly goes away. Okay? This here? Oh. I'm so glad that you're catching my sloppy morning mistakes. This should be bigger than 0, smaller than 0. That's more like it. Thank you so much for that. Now, let me raise the screen here. And thank you so much for enduring the math. We have just one more thing we want to put in our toolbox, and then we can have fun talking about how we can apply this and why it's useful. So, first of all, there's something really funny about this. If you plot versus redshift, and you plot the angular diameter distance, as expected, at low redshift, it starts to rise linearly. That's what you expect just in traditional Newtonian space. If twice the redshift means things are twice as far away, so it should be twice as far away, right? But eventually, when you work this out for any reasonable cosmological parameters, it actually turns over and starts going down again, typically at a redshift of around 1. And that actually has a crazy implication. That means if you take my phone and you ask what angle does it subtend, I keep moving it farther away. It looks smaller and smaller and smaller. What's going to happen when I start moving in far beyond redshift 1? It's going to start looking bigger again. Very surprising. So actually, very distant galaxies and galaxy clusters actually look bigger again. Why is that? In other words, this angular diameter distance is actually it acts non-Euclidean. Well, there are actually two separate reasons for it. First of all, our universe was much smaller in the past. Right? So even though, if you look at our universe here that has been reinflated, you can look at the angle between here and here in the sky, and it's 90 degrees, right? It looks huge. But those two parts are not very far apart from each other, because our whole universe was only 400,000 years old there, right? So the distance between those two places are only in the ballpark of 400,000 light years, or a bit less, right? So it's kind of shocking that something as small as 400,000 light years is going to subtend 90 degrees in the sky if you put it, 13.8 billion light years away. But the reason is that space itself was smaller, and it's because of this that things ultimately started looking bigger. So that's the first reason. A was smaller in the past. There is also another reason. Space can be curved, and curved space can also mess with angles. We'll get back to this in more detail soon, but generally if I have a triangle, and if I draw a triangle on the surface of an apple or something, and I measure the three angles of it, they're going to add up. I'm going to get that the sum of these angles are going to be bigger than 180 degrees. Generally, if you have spherical curvature, things look bigger. It's the same thing here. For a given redshift, any given object is going to subtend a larger angle if you start curving space. A very non-Euclidean kind of thing. Okay? So now we've talked about the toolbox for figuring out how big things look. We also need to say a bit about how bright things look. Because that's what these guys got the Nobel Prize for when studying supernovae, right? They measured how bright they looked. They knew how bright they should have been. They used that to infer the actual distance to them. And then they used that in turn to conclude that there was dark energy in our universe. So how bright do things look? Well, in kindergarten, you all learned that the flux of something obeys an inverse square law. So you take the actual luminosity and then just divide by 4 pi times the distance to the thing squared. Because this is the area of the sphere on which the light has spread out, right? So in following the tradition of what we did here, just taking the classic formula and just defining an object, the angular diameter distance, kept the simple form, we'll do the same thing again. We're going to now define something called the luminosity distance and let it depend on redshift, such that the flux goes like the luminosity divided by 4 pi, that thing squared. Okay? And this time, the good news is that the formula for the luminosity distance, even though it's also complicated, is complicated in almost exactly the same way as the angular diameter distance. There's just a different dependence on redshift. Sorry. dA of z, 1 plus redshift. So we don't need to do any more math for this. Okay? And if you ask here, why does this behave non-Euclidean? What is it that's new with general relativity and cosmology about how bright things look? Well, it behaves differently than luminosity is in classical non-expanding space, both for this reason, that's again, A was smaller, space was smaller, the scale factor was smaller in the past, and because space was curved. But there are also two other reasons. That's why you get this extra redshift thing here. It's because, in addition, the photon arrival rate changes. Things are redshifted. If you look at a very distant object, if you look at something at redshift 1, a supernova exploding at redshift 1, you see it actually blowing up at exactly half the speed. can think of it as a time dilation effect from the high speed, or you can think of it as gravitational redshift. That means that even though it thinks it's sending off 1 photon per second, you're only going to get 1 photon every 2 seconds. So that gives you a factor of 1 plus z loss in brightness. And then also each photon that arrives is only going to have half the frequency, right? Because of redshift. So we have photon redshift. So that's another 1 plus z factor you lose. And since you're supposed to take the square of the luminosity distance, you get 1 plus z and 1 plus z. So even though these formulas are a little messy, you can see that there are simple physical reasons for all of their funky and eclectic behaviors. So let's just summarize here our toolbox, okay? So there are things that we measure. Like redshift, like the angular size of something, how many degrees it subtends in the sky, or arc seconds, and the brightness of something, how many watts per square meter of light you get from it, or energy. And then there are things that we want to know as physicists about it. What do we want to know? We might want to know, instead of the redshift, we might want to convert that into the actual distance. We might want to know the distance to the object. Or we might want to know the so-called look-back time. How long ago was it that the light was given off? Okay. That's all taken care of by the first equation we derived here, right? And then we might want to know, instead of, we measure the angular size, but we might want to actually know the transverse physical size. How many light years wide was it? And we measure the brightness, but we would like to connect that to the physical property, the luminosity. And we've now looked at all of the key equations for this. So why exactly did Saul Perlmutter and Adam Rees and the others, why did they get the Nobel Prize? Because they looked at all these supernovae. They measured their brightnesses super carefully, measured their redshifts. And then they made very careful modeling of how luminous they really were. And then they did all these integrals. And then they did a fit to all their data and found that they can, to fit all the data really well, they needed to have an omega lambda, which was about 0.7. With pretty small error bars. So they wrote this paper. So they said, hey, there is dark energy in our universe. That's how they did it. The astrophysics of the understanding the explosions was a bit complicated, but as you can see, the math is really not very complicated. And just beautiful general relativity. So let's now, that you've so patiently endured all this math, take a look at the data. Because if you just have a bunch of theory, you can predict all these things, but you can't test anything, the whole field tends to stagnate. That's the state that cosmology was in for a long, long time. Right? But we've been so lucky in cosmology that we have all this wonderful data. And I want to do a quick survey now of a bit of the awesome things that have been happening here. So, for example, we talked about supernovae. Boom. Let me make it even darker so you can see. Again, a supernova go off. Here's a galaxy. Let's see if I can. A distant galaxy. And as the supernova explodes, you can see briefly it outshines the whole. It shines almost as brightly as the whole other galaxy. On the right side, you see how the brightness rises and then dims again over the course of days. And how the observers also very carefully measured how much light comes out of different frequencies. And by looking at those additional details, they can further calibrate exactly how many watts it was. Okay? That's one cool application of this luminosity distance. Nobel Prize worthy. Another really nice application, and the most famous application of the angular diameter distance formula that we talked about here, is the cosmic microwave background. So who is the keeper of our universe right now? Can you toss it down? You'll have to help relay. Oh, nice throw. Universe in motion. So we'll talk more about this next time. But you see all these characteristic spots here, right? We see them when our universe was about 400,000 years old. So if they're caused by some actual local physics going on, no effects could have really causally spread more than about 400,000 years, 400,000 light years. And as we'll see, the speed of sound was in the ballpark of the speed of light back then in this plasma. So in fact, you expected there to be a characteristic size of these blobs of about 400,000 light years. So you have this wonderful situation. There is something, namely a blob, or the average blob, but you know its size. You know the size is 400,000 light years, say, and then you can measure the angle it subtends in the sky. And then you can use the angle diameter distance formula and say, okay, what does this tell us now about cosmological parameters? This is the all-sky map from the Planck satellite. This is doubly mapped, so we have even sharper vision here. And I'll talk a little bit more about specifically how this power spectrum curve is defined, but the fact that this first peak here sits at about 1 degree means that when you make the prediction, when you make the measurement rather, you see that the typical blob size is about 1 degree, about twice the size, the angular size of the full moon in the sky. Okay? Now, what does theory have to say? Well, that depends on these cosmological parameters. If you go to my website, let's see if we can zoom out so you can see this with lower resolution. Awesome. If you go to my website and you click on technical and then you click on C&B movies, I have some little movies here that I made, and then grad student Chris Williams helped further improve, which shows, for example, the microwave background power spectrum. And the blue here and purple are measurements. That's data. Okay? The red curves are theory predictions. I'll talk more about where they come from tomorrow. But notice the red curve is changing. Why? Because I'm continuously changing omega curvature, the curvature parameter. And what is that doing to the red curve? It's kind of stretching it out so that the peak is moving to the right to smaller angles. The x-axis is inverse angle. What is the deal with that? Well, remember we just talked about how if you curve space, all angles look bigger? The rigorous way to show that is to look at the formula that we had here. This is the angular diameter distance. There is a omega curvature in there. You can take the derivative of this with respect to that and verify for yourself how exactly the angular diameter distance changes. But take my word for it for now. This is exactly what happens. If you take a spot that's 1 degree in size, and then you just imagine you have this knob in your calculation. You do it with Mathematica or something, and you just start changing the curvature parameter. What you'll find is the predicted size of the blob that you're going to see measured in degrees gets smaller and smaller if you make space more and more negatively curved like we're doing here, more and more hyperbolically curved. That's awesome, because we can turn that into a measurement of how curved space is. Right? This is how, for the first time ever, we got really good measurements of the curvature of space. Another way of thinking about this is make a triangle, measure the 3 angles, see what they add up to. Here we're making the biggest triangle you can imagine. It goes all the way from you, 13.8 billion light years, over to one edge of a C&B blob, over to the other edge of the blob, back to you. Right? And this is more complicated because, in practice, because you see this formula for angular diameter distance also depends on this integral of h of z, which also depends on other things. So if I instead change, for example, the dark energy density, That also changes a bit, you see, the size of the blobs. Effectively, that's changing the distance between you and the blob, which will also angle that in a different way. So now it's going to look, again, bigger or smaller. So it's a little bit harder than this. You actually have to make a joint fit. You twiddle all the knobs and see if you can get a fit to the data, and then you do joint constraints. But the data are now so excellent that even taking these complications into account, we can actually measure the curvature of space to better than 1% precision. So that's another fantastically successful application of this idea. Luminosity distance gave us a supernova triumph. Angular diameter distance, C and B blob size, let us really nail the curvature of space. And also tell us about dark energy and give us a sort of independent measure of that number, in fact, which is very cool, because in cosmology, for many, many decades, sort of in the early dark ages of cosmology, what you would have is a situation where someone would write a paper saying, we've measured the Hubble parameter h. It's 50 kilometers per second per megaparsec, plus minus 4. And that will be all fine and dandy until you saw someone else's paper who said, we've measured it even more accurately. It's 100 kilometers per second per megaparsec, plus minus 3. So all you know for sure is that somebody is wrong. And Landau even famously said that astronomers are often wrong, but never in doubt. and to further embarrass myself here in my community, when Edwin Hubble first wrote his very first paper on saying, hey guys, the universe seems to be expanding, the Hubble parameter is, you know what the value was he quoted? 550 kilometers per second per megaparsec. That turned out to be a factor of 8, a factor of 7 or 8 bigger than it actually was. Okay, so when people calculated the age of our universe, then from Edwin Hubble's value, they got about less than 2 billion years. And some geologists got really pissed off about that, because they would be like, dude, I have a rock here. I have uranium dated my rock. It's 3 billion years. And you're saying our universe is how old? And that's why this amazing avalanche of new high-quality data has been so important. Because now we can not only measure things really accurately, but we can measure them in multiple ways. And they actually agree. For instance, supernovae folks got 0.7 roughly for dark energy. Well, by combining the micro-background stuff and galaxy clustering, like I tell you about tomorrow, we independently were able to measure the dark energy, and we also got 0.7. It's pretty awesome. Now, when you use the micro-background and things like this to measure the Hubble parameter, you get about 0.7, or 70 kilometers per second megaparsec. And when you use the Hubble Space Telescope and do it the old school way by looking at galaxies flying away, you also get about the same answer. It's very reassuring. If you ask, what's the percentage of atoms in our universe? If you do it the micro-background way, you get 5%. If you instead do it by looking at what I mentioned briefly yesterday, the period when our whole universe was a fusion reactor during its first few minutes, and produced 25% helium. For it to produce the right amount of helium, and deuterium and lithium, you need it to be about 20. Also, you need about 5% atoms. So you can measure 5% two completely different ways, totally different people, totally different data, different assumptions. It agrees. So the precision data is what's really transformed cosmology, I feel, into a real science. Yeah. Absolutely. I was going to talk more about micro-background tomorrow. So let me just say very briefly today that the error bars here on this curve include uncertainties from just measurement noise, electronics in the receivers and stuff, and also something we call sample variance. So what we're trying to measure actually is what you would get. What the theory predicts is what this curve would look like if you built an infinite number of Planck satellites and launched them on infinitely many different planets very far apart in space. We haven't gotten the funding to do that. We can only build one. So we only have a finite amount of space we can look at. And because of that, you get additional errors. It's kind of like if you do a poll and you ask, how many percent of Americans think that it's a good idea for the government to be reading your emails or storing them forever or whatever. If there's a poll and it says 50%, they'll have an error bar on there. If they asked all Americans, the error bar would be 0, right? But you try to estimate what fraction of all Americans there are by asking only a small sample. And this becomes more and more important when you go to the left, because now you're probing very large-scale fluctuations, and there are not a lot of sort of very large-scale patterns in the sort of finite sky. But we can talk more about that tomorrow. It's particularly annoying because the only place where the data does not fit the theory well is on the large scales, and their error bars are the biggest. And it's hard to do much better unless we can go to another universe and take data there. Yeah.
So, just to be clear, these error bars, so-called standards.
Yeah. No. You would need to go to far away out of our observable universe and build and observe there. So you get to the fresh parts of space you haven't looked at yet. Unfortunately, no. Working on it. No. Yes. There is something we can do a little bit better on. We can measure the whole interior of this also, which I'll talk about tomorrow with 21 centimeter tomography, rather than just do this kind of two-dimensional measurements. So we're not done, but we are beginning to bump up against certain quite fundamental limits on what we can know. One other application I just want to mention. Yeah? There are a number of sort of slightly strange things that have been discovered here on very large scales. First of all, the overall power seems to be, there's a little bit too little fluctuations there by about 10%. And second, our universe doesn't seem to have a special direction. It tends to look the same everywhere, except on very large scales where there seems to be kind of a special direction. I actually discovered this very inadvertently late one night when I had worked very hard together with Angelica Oliveira Costa and Andrew Hamilton on a new algorithm for cleaning out the galactic radio noise from these maps, which is making this red band here. And so I felt for the first time I had a map now which was clean enough that one could do this analysis in the whole sky instead of having to always throw away a third of it. So I wrote this program to calculate this like that. And then I thought, and sure enough, this point was too low. So I thought, but I want to see what it looks like on the sky, because I'm a very, very visual guy. So this is the way you actually do it, is you do a Fourier transform of the map, but a spherical one. You expand it in spherical harmonics. So I just wrote this code which expands the map in spherical harmonics and plots it for me. Typed in 2 for the quadrupole, pressed enter, and sure enough I got this picture. It looked very anemic, a low thing, but it had a weird shape. Instead of looking kind of isotropic, equally messy everywhere, all the action was in a certain band around the sky. And now it was like 3 in the morning, and I was very tired, but I thought, I wrote the code. Before I go to bed, I'm going to type in 3 also and see what happens. So I did that. And again, just a weird band came out like this. It didn't look at all isotropic like it was supposed to, and it was aligned with a quadrupole. Very strange. So I thought I must have put a bug in my code. So I typed in 4. And now it came up looking totally normal. This is very confusing. We just put in a little section at the end of our paper and said, oh, and by the way, there's this funny alignment of the quadrupole and the octopole, as we called it. Later on, other people studied this much more and gave it this catchy name, the axis of evil, and found that it was even more significant than we had found. And it's still there in the Planck data also. So for a long time, you could wonder whether the WMAP team had just done something weird. And there was even a Chinese group that made a very serious analysis where they had an idea for what might be wrong in the WMAP analysis. But it's there in the sky. And since then, people have also discovered that there's it looks like there's more fluctuations on one side of the sky than the other. And we still don't really know what to make of it. It could be just nature having fun with us, creating a big fluke, to throw us off. Or it could be, the most exciting possibility is that this is telling us something about the beginning of inflation. Because as I'll tell you a bit about later if I have time, the best theory we have, right, for what made this was inflation. And inflation made the fluctuations on the larger scale first, the biggest blobs, progressively made smaller and smaller ones. And if inflation had been going on for a very long time before it made the stuff we can see, all information about how it started and that high energy physics is basically lost. As if, like, if you walk into a bar and there are two guys fighting, if they've been fighting for a long time, you can't even tell who started or why or anything. It's reached some kind of steady state equilibrium of just idiocy, you know. But if you walk in, like, after the first 5 seconds, there are still a lot of clues you can see that might give you insight as to why this began. And it might be, if we were lucky, that we kind of walked in on this cosmic brawl here early enough that we're actually seeing something that happened very early on in inflation. So by studying these anomalies more, we might actually learn more about the physics of it, which would be very cool. Good. Just to summarize a few more of these observational things. This idea that you can measure some characteristic scale in the sky, angular scale, and then compare that with a predicted angular diameter distance and use that to fit parameters, can be done now not only with a microwave background, where you're looking at these blobs at redshift 1100, but it can also be done closer by. If you look at galaxies very carefully at how they're clustered, it turns out there's a sort of characteristic scale where they're a little bit more clustered. This was first measured by Daniel Eisenstein and collaborators in our Sloan Digital Sky Survey project. So you can, again, play exactly the same game, but because you're doing this now at a different redshift, you can break a lot of these irritating degeneracies. Before you saw that when we looked at how the size of the microwave background blobs depended on these interesting parameters, you saw it was a little bit complicated. You can shift this power spectrum left and right by changing the curvature, also by changing the dark energy, or by changing its equation of state, and so on. But the galaxies, they also get messed up by all these different things, but in rather different ways. If you look at the galaxy curve here at the bottom, never mind the details, they're completely irrelevant for what we're talking about, but simply because you're integrating out to a different redshift, you're measuring different combinations of these same parameters. So it's kind of like you have many different equations with the same unknowns. They're independent equations. That helps you invert and solve for all of them. So this has become a new major cottage industry which goes by the name of BAOs, or baryon acoustic oscillations, where you try to look at the galaxy clustering at many different redshifts and measure this special pattern. And then, as I mentioned very briefly, by studying Big Bang nucleosynthesis, the cosmic fusion reactor, you're actually also probing exactly the expansion history of our universe, because it turns out that if our universe expanded a little bit faster or a little bit slower, that would determine how quickly the fusion reactor shut off and how effective it was. And if you calculate the yield, how much you produce of these different elements, it depends on how fast the universe is expanding. So let me just show you, when you put all of this together that we've talked about today, what have we learned about this function? So the whole quest is, what is A of t? Right? What is the cosmic expansion history? Is our million-dollar question. We would like to know this curve. How has our universe expanded as a function of time? A more convenient curve to look at is if you just take the logarithm of A and then take the time derivative of that, which is h, right? And then just say, okay, let's just go measure this Hubble expansion rate as a function of z. This is more convenient. It's mathematically equivalent to this. If you know this curve, of course, you can solve for that curve. If you know what this curve is, you can solve for this. But this is more closely linked to the observations, because we always measure the redshift of things. And this h is what enters in all our integrals all the time. So let's talk about, what do we know about this? From all of the cool measurements we have, what have we learned? Well, that's what I'm showing you in this plot here. Remember, the Friedmann equation says that h, if you square this, you just get the density of our universe. up to some stupid pi factors and stuff, right? So the density of our universe as a function of redshift just goes like h squared, aside from curvature, but the curvature basically seems to be 0 anyway. It's a good approximation. So let's plot the density instead, because it's the more physical thing to think about, as a function of redshift. I'm plotting redshift going backwards, so I'm actually plotting A now on this axis. And notice, first of all, this is a ridiculously extreme scale of the kind we only get in cosmology, where this axis goes 60 orders of magnitude on the log scale. Our universe has gotten 10 to the power 60 times bigger from here to here. And the density has dropped by almost by over 100 orders of magnitude here. So it's a pretty nutty scale. What have we learned? Well, we think that this curve, which summarizes everything about our universe, the 0th order, the cosmic expansion history, has gone something like this. Let's drill down and look at it a bit more closely. Matter-dominated means the slope will be -3 in this log-log plot, right, like we worked out last time. Radiation-dominated means slope -4. Vacuum-dominated, dark energy taking over, means slope flat here. Here, I've zoomed in a little bit. This is from a paper I wrote with Yoon Wang. We took all the data and fit it and said, this is what the actual density has been doing. We know that there is matter that exists, so if you subtract off that part, you can plot the density of the leftover, the dark energy here in green. These are 1 sigma errors. And it seems like we didn't even assume anything here about the dark energy being constant. We just said, this is what we know about how dense dark energy was versus time, and you see it's consistent with being completely constant. And to this day, it still is. So the million-dollar question for dark energy is it constant? If you can make any kind of measurement that shows that the dark energy is changing its density with respect to time, or with respect to space for that matter, that's probably worth the free trip to Stockholm. And if we go up and look here instead, high redshift, we know less about it. We can go back to the first second or so, Big Bang nucleosynthesis, and say the curve looked like this. But then inflation solves all these other problems about explaining why there was a Big Bang, and the horizon problem that some of you discussed with me after a class yesterday, and so on. If you assume that this curve actually bent over like that, and had another phase where the density didn't dilute much, okay? Exponential expansion. If that happened, the story is something like this. But this is much more uncertain. We don't know if inflation happened at all. If it did, we don't know the energy at which it happened. It could have happened, for us to have any clue what we're talking about, it must have been much below the Planck scale. In fact, we know it must have been about this much below the Planck scale. Otherwise, it would have predicted gravitational waves of a much greater amplitude than we've already seen. We also know that it probably happened well above the TeV scale, because otherwise you might see new physics at the LHC to do with inflation. Or starting to create inflationary universes in Geneva or something, which would be pretty weird. But this is much more uncertain, what's going on. Okay? What's also very cool is, if you read more about inflation, the single most important thing to take away from it is that inflation is a very violent process, which really sort of shakes up the whole very fabric of space-time and produces ripples in it of all sorts, including ripples in the fabric itself, so gravitational waves, in other words. And the amplitude of these fluctuations turns out to be simply equal to the height of this curve, to the density in Planck units. So it's a very, very convenient thing. If we can ever measure, that the really big thing now in microbackground research is to try to look at these maps through a polarizer and see if you can find this very characteristic pattern of gravitational wave fluctuations which have distorted these patterns in a special way. If you look at me while a gravitational wave flies through this classroom, I might look distorted like this, right, in some funny way. That's the principle behind the LIGO detector and all the other gravitational wave detectors we build on Earth. The microwave background will also be distorted. If a super long gravitational wave of wavelength comparable to our universe flies between you and this plasma surface, the pattern here looks distorted. And it looks distorted in a very particular way from these gravitational waves that inflation makes, and everybody's looking for them. If someone can find them, it'll be a direct Nobel Prize, and probably also a Nobel Prize then for the pioneers of inflation, because we don't know any other process that has the ability to create these kind of things. And the coolest thing of all is if you can measure that, it directly tells you how to extend this curve. It would tell you from the amplitude of these exactly how high up the curve goes. And by looking at the amplitude of different scales, large blobs, small blobs, you even get the slope of this curve. So you can see how inflation proceeded, which would be absolutely, absolutely sensational. The amplitude, for example, would be 10 to the minus 6 if the expansion rate h divided by the Planck scale is 10 to the minus 6. And so in summary, what have we done so far? I've shown you a bunch of basic tools for how to connect simple theory with all these state-of-the-art experiments, and said that we've gone now, we humans, from knowing almost nothing about the history of our universe to having actually very precise measurements of a lot of these parameters, of the age of our universe, and we've reconstructed that to zeroth order, our universe, we think, went through something like this. And the future directions that people are very actively focused on is particularly drilling down here to see, can we look at this more carefully to understand better what the dark energy is up to? And can we measure the curve better up here to learn about inflation, to learn about super high energy physics that we could never get funded at the LHC study by using our Big Bang itself to probe what happens near the Planck scale at 10 to the minus 34 seconds, all of which would be really awesome. Thank you.